So far we have dealt with vectors that originate at the origin. What about vectors that originate at other points in space? For example, if I have a board with two forces acting on it, it's possible that these two lines of actions do not intersect. And so I can't define an origin to go back to the line of action for both of these forces. That problem becomes even worse if I start adding other forces. So we have to learn to deal with vectors that don't originate at the origin. In addition, we may need to define the information that relates the relative location of 2 points in space. So we may need to relate the relative location of this point in space, or where the force F1 is acting, to this point in space, where the force F2 is acting. In the previous video, we learned one way to write a vector is the magnitude times a unit vector. So if we were to write a vector R, we recognize that we could express it as the magnitude R times a unit vector that describes the direction of R. This representation explicitly demonstrates the two pieces of information a vector provides: the magnitude and the direction. A position vector provides this information for 2 points in space. One can think of it as telling you how far to go, or the magnitude, and in what direction to go, or this unit vector R, to get from point A to point B. So how do we obtain a position vector? First, we recognize that what we're talking about is going from point A to point B. And this vector tells us how to go from point A to point B. So there is a vector that extends from point A to point B. Next, we recognize that there is also a vector that goes from the origin to each point. So the vector goes from the origin to point A, we'll call vector A. The vector that goes from the origin to point B, we'll call vector B. If we take this triangle and look at it, we should be able to recognize that what it defines is vector subtraction. This vector, R, A to B, R, A to B, is minus A, because to get from its base to its head by traveling along these lines, you have to go in the minus A direction and then go in the positive B direction. So it's minus A plus B. We can rewrite that for simplicity as B, minus A. Expressing A and B in Cartesian notation and doing the math results in a simple formula to calculate the position vector that describes how to get from point A to point B. Bx minus Ax in the I direction, By minus Ay in the J direction, and Bz minus Az in the K direction. Note that Ax, Ay, and Az just represents the coordinates of point A with respect to the origin. Similarly, Bx, By, and Bz represent the coordinates of point B with respect to the origin. Now imagine that a rope is anchored at point 1 and is being pulled with a force of magnitude F at point 2. We can write the force as a vector by recognizing that it's nothing more than the magnitude that we're given times a unit direction, a unit vector that defines the direction. The position vector for the rope that tells us how to go from point 1 to point 2 is nothing more than the length of the rope times a unit vector that defines how to go from point 1 to point 2. We now know that UF and UR12 define the same direction. In both cases, we're going this way, right? So maybe that's going towards France. Okay, they define the same direction. That means that we can replace UF with UR12. So F is now the magnitude times UR12. We also recognize that this unit vector is the vector, the position vector that describes how to go from point 1 to point 2, divided by its magnitude. That means that F can be written as the magnitude of F times this ratio. To find the position vector that defines how to go from point 1 to point 2, that ratio is nothing more than x2 minus x1 in the I direction, y2 minus y1 in the j direction, z2 minus z1 in the k direction, divided by the magnitude, which can be calculated by this value in the denominator. So now we can provide only the magnitude of a force and separate information, for example, where the rope is, that defines the line of action of the force. The final concept from Chapter 2 is the dot product. The dot product is also called the scalar product because it results in a scalar, not a vector. So in general, the dot product, A dot B, is defined as the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. So if I have a vector A and a vector B, the angle between the two vectors is defined as theta. And it's actually used to find the angle between two vectors in three-dimensional space that start at the same point. If we have both of these vectors written in Cartesian notation, we can prove to ourselves, which we won't do here, that the dot product is equivalent to AX times BX plus AY times BY plus AZ times BZ. Therefore, the cosine of theta is equal to AX plus BX plus AY times BY plus AZ times BZ divided by the magnitude of A times the magnitude of B. The dot product can also be used to find the component of a vector parallel to a given direction. For example, if we have vector A and we want to know what component of that vector is parallel to this direction, which we'll call B. So this is not a vector, this is just a direction at this point. So we want to decompose A, but the only thing we care about is the piece of A that points in the B direction, right? All we need is the angle between the A vector and the B direction. So now we say A dot B, but we use only the unit vector that defines the B direction. So the unit vector that defines the B direction is equal to A. The unit vector has a magnitude of 1 cosine theta, and that is equivalent to the component of A in the B direction, only its magnitude. Well, how do we determine its direction? Its direction is the same direction as B. So AB is equal to the magnitude of AB times UB, which is equal to A dot UB times UB. This concept of the component of a vector in a given direction is also referred to as the projection of A onto B. And you'll note that cosine of theta is equivalent to A of B, or the projection of A onto B, divided by A, as you would expect from the definitions of cosine in a right triangle. As always, if you have questions about this, please come see me.